All right, so our presenter today is well-known friend of Lunar Volatiles, Shuai Li from the University of Hawaii. And without and Shuai is going to be talking to us today about some recent work on the formation of lunar surface water when the moon is in Earth's magnetotail. And so before I hand it over to Shuai, I'll just remind everyone, if you're not speaking, please make sure your microphone is on mute. And Shuai, would you prefer if we wait until the end for questions, or do you prefer if people put questions in the chat or speak up in between? Either way
Yeah,
is fine.
either way is fine. Yeah, it doesn't matter.
Okay. All right. So in that case, maybe I'll say if it's if it's a brief question, maybe go ahead and put it in the chat. And if it's a longer question, we'll hold it until the end. But without further ado, I will hand it over to Shuai. So Shuai, take it away whenever you're ready.
Thank you, Parvati. I'm so glad to give the last talk of the session for this year. So the title of my talk is the new formation processes of lunar surface water in Earth's magnetotail. You can see the difference. The bottom is the screenshot of our paper title. You can see the difference. This is the debate between me and the editor, because the editor said when you say new, that means like it never happened before. I realized it should be like a previously unrecognized formation processes of lunar surface water in Earth magnetotail, or the more direct way to say it is formation of lunar surface water associated with the high energetic electrons in Earth magnetotail. First, I would like to thank all my co-authors who contributed a lot of discussion to this work. I will mention them later in the talk. Okay, so I think we all know these kind of work. In the past over 50 years, there are tons of analysis of water in retained lunar samples, and it suggests the solar wind origin is a dominant source. As you can see from the left figure, this is a hydrogen profile measured in lunar regolith grains from the surface to interior. You can see it's a peak at the top, like a few tens to 100 nanometer top surface grain rims, while the less exposed interior grains, you don't see such a trend. So this is consistent with the hypothesis that this is due to solar wind implantation. And in the bottom figure showing the hydrogen isotope measurements from agglutinates in Apollo samples, it shows the isotope signature is so close to the sun. So the conclusion from this paper is that water in these kind of agglutinates, trapped in the agglutinates, are mostly from solar wind. On the right figure showing the most recent analysis of Apollo samples, it's Chang'e 5 samples retained like 2 years ago. They measured both the hydrogen profile from the surface of the grain to the interior. Similar to the first work, you can see mostly concentrated on the top, like a few tens to like 100 nanometer depth on the surface grain rim. And also they measured the hydrogen isotope. It suggests to be very close to the sun. So also conclude that most of lunar surface water in the lunar regolith should be from solar wind. And their orbital measurements suggest that the formation of water by solar wind could be instantaneous. I highlighted the keyword instantaneous. This is exactly the word used in Jessica Sunshine's paper. This is on the left. I'm showing a figure from that paper. It shows two different regions. One region, the red region, shows no water, while the blue region shows water absorption. They are close to each other. The blue region is closer to the terminator. So it means it's cooler, and this suggests the water formation can be instantaneous. And on the right, showing a figure from Chris Lafayette, recent paper, they dive into the DI data and did a more thorough analysis showing the same thing. You can see the water on the morning and afternoon is higher than local noon time. And it also suggests water formation processes could be very fast. Okay, both of these kind of like a previous work, I developed a hypothesis, a question. So does water formation stop in the magnetotail due to the shut off the solar wind protons? Because the moon orbited the Earth, and each lunar day, the moon goes through the magnetotail, and we know the magnetotail is formed due to the magnetic field. So figure A shows a set of view of like a schematic set of view of the lunar moon orbit, and the simple configuration of the magnetotail. What you can see here is during the orbit of the moon, it travels from the solar wind and into the magnetotail, and then first it goes to the magnetosheath. So this is where the solar wind pushes the magnetic field line. So there are like a denser charged particles in the magnetosheath, and then go into the magnetotail lobe. The magnetotail lobe is kind of like a void space. There are very few like charged particles, and there are two parts, like you can call it like a north lobe or south lobe, and there is a plasma sheet separate them. So this is a 3D view. So just projected in a 2D, but you have to imagine it's a 3D. So it's like a ball. There are north lobe, south lobe, and there's something in between. There's a plasma sheet. And that plasma sheet is highly variable, and there is no clear boundary between the lobes. And then go to the magnetosheath again, and go to the solar wind. So there are Artemis measurements of charged particles, particularly like protons. And on the right, I'm showing the profile, the solar wind ion flux versus the lunar phase. What you can see here, when the moon is in the solar wind, is like 10 to the 8th. That's what we know. And then goes to the dusk. That's the ion flux increased by 50%. And then it goes to the magnetic lobe. When the moon is in a lobe, it's like less than 1% of charged particles, like protons, than in the solar wind. So this is where I developed this hypothesis. So does the moon formation stops when the solar wind protons drops to like less than 1% of a solar wind, when the typical solar wind? And also I'm interested to know how the water abundance varies with this flux curve. Because we know the formation, from previous slides, it suggested that the formation is instantaneous of water, and they should show like a correlation with the flux variation. Some methods, details. So I'm going to use the well-known moon mineralogy mapper data to map the lunar surface water. I'm going to rely on the OH fundamental stretching and H2 vibration over time, both near the 3 micron. So this is how the N-cube spectrometer look like. This is assembled to Chandrayaan-1 mission. And on the red figure showing like a typical lunar surface minerals, how their spectral looks like, and also the coverage of the spectrometer. I want to highlight the most red side. That's the greenish box showing where the water absorption show up. So this is due to the fundamental stretching and also the first overtone of H2O. So that's why, because they overlap, so that's why we cannot tell the species clearly, because the overlapped absorption. And there are a few challenges. The first well-known challenge is a thermal correction. I'm showing one example here. So the red curve is the raw data and cube IOF data without any correction. And then there is a dot line, black dot line. This is a released IL2 reflectance data. This is an example showing like it's corrected for the thermal correction. So you don't see any absorption feature. And then we derived we use the divided bolometric temperature at this region acquired at the same time with M-cube data. Did correction issues as the blue plus line. And then we plot Apollo 17 glass as a comparison. You can see the absorption, first absorption of water show up. Second, it's consistent, the shape and the position consistent with the lab data. So to do the thermal correction, we use an empirical way. This is based on the observation of the lunar spectral data in lab. As shown in the left figure, you can see the most parallel, so they rarely cross over with each other. Then we came out at this idea to pick up 2 different bands, one without any thermal effects and also no absorption, so cannot be affected by any absorption. And the other one is in the thermal region, but also there's no any absorption can affect it. Now we plot them together. You can see in the middle figure, they show a very tight trend. So the reflectance between 1.55 and reflectance between 2.5, they show a nice trend. This is like over 600, yeah, somewhere close 600 Apollo samples. And you can imagine when there is a thermal component, they will fall off the trend, above the trend. And then any additional like energy we can attribute to thermal emission can remove it. It turns out the thermal effects at this band is very sensitive to temperature. This is a demonstration on the red figure. I'm showing like only around like a 10K overcorrection. I'm showing the pink line. You can see the absorption feature is drastically different from those Apollo samples and also those appropriate corrections. And we use this as a further constraint of the correction. So this is on the bottom figure. I'm showing an example, like analysis of like a few hundred Apollo samples showing where the water absorption start to show up. It's occurred in a very narrow range, like around 2.68 micron. And turns out this is very temperature sensitive. So we use this a very powerful constraint for overcorrection. And then another challenge is the albedo dependence of the absorption feature. So this is well known in the community, but it's also like confusing. I see so many papers talking about, oh, they observe band depth dependence on the Murray and Highland. But I want to point here is like, it doesn't necessarily mean the absolute water content is different, even though the absorption band depth is different. Here's one example on the red figure. I have two samples. This is used in my thesis. One is a pleasure clays, the blue line, the blue solid line. Look at the solid line first. The blue solid line is a reflectance of pleasure clays near 3 micron. The red solid line is marble glass near 3 micron. And both of them are similar particle size and a similar water content. Well, after continuum removal, you can see the dashed lines. The band depth of another side, the pleasure clays, is around 30% more than the basaltic glass. So this is a well-known albedo dependence. So this is due to nonlinear mixing of the matrix. Like say the basaltic glass is darker when it mixes water absorption. The matrix plays a bigger role than the pleasure clays. So that's why the absorption depth is smaller than the pleasure clays. So and also it's well known. The Highland is around like 2 times brighter than the Murray region observed in the Lunar albedo. So that means like, even though I see this, even though there is same amount of water in Murray and the Highland, you still expect to see the Highland absorption depth is deeper than the Murray. This is because of albedo dependence. This is because of the nonlinear mixing issue. So that's the challenge. So when you see the paper saying, oh, there is a albedo dependence in the band depth between Highland and Murray, and it should be cautious. That's just band depth. Doesn't mean the absolute water content is different. And to overcome this albedo dependence, we convert reflectance to single scalar albedo to reduce the albedo dependence. I wouldn't say like a completely remove it, but it can be significantly reduce it. And then we use a happy parameter called effective single particle absorption thickness. This is very simple. So you do a continuum removal of your single scalar albedo and then calculate the band depth. So this is still the same similar algorithm, but it just converted to single scalar albedo first. And then I use a bunch of different samples, marble glass, andesite, synthetic volatiles glass, and to get this empirical trend on the red figure showing the absolute water content versus the absorption strength near 2.85 micron. This is about absorption center of water. You can see like even though the composition are different from each other, and they show a very tight trend. They follow almost the same line. And then we use this empirical trend to derive the absolute water content on the lunar surface. And the first thing we did is validation. So because we have now have Apollo samples and also Channel 5 samples, so we did 2 different types of validation. First one is Apollo samples. This is on the bottom plot. showing this in the past 50 years, they run like over 100 measurements, like very reliable measurements of water in Apollo samples. Even though most of them has been exposed to the atmosphere, I tried to set up a temperature threshold to assume part of the water, like when the temperature is low, I assume the water is from the atmospheric contamination, and I use the water derived at a higher temperature. Anyway, it shows a great consistency. The gray histogram is from like the average of water in the sampling latitude zone of Apollo samples, and then compared with this red and green histogram that's from those individual Apollo sample measurements, just by different ways. One is the red one is from SIMS measurements, the green one is from pyrolysis measurements. Well, recently, this is still unpublished. This is from Lin et al. This is in preparation. I just grabbed the figure from that manuscript. What you can see here, this is from sealed channel 5 sample. I use spectrometer, measure the spectra, derive the water content based on the previous empirical model, and versus the SIMS measurements from the same channel 5 regular screens. You can see this shows a great consistency, and also it shows a clear particle size dependence. So this is additional like a validation of our mapping results, mapping algorithm. And for data used for this study to assess how the water varies in magnetotail, I use all M-cube data because to get the best coverage during the moon passage through the magnetotail. And second, I just empirically split them into 6 different lunar phase period to bin the data, because if you just examine individual like a lunar phase, that wouldn't be enough observation. So I just split them into 6 phase period. The first one is in the typical solar wind. The second one is in the dusk magnetosheath. The third one is in the first half of magnetotail. The fourth one is in the second half of the magnetotail. And then the fifth one is in the dawn magnetosheath. The sixth one is in the typical solar wind. So based on the observation of these 6 phase periods, I want to derive how the water variation versus this solar wind flux. And also, this is based on the observation at the same location. So we don't have to worry about like a latitudinal or optical maturity dependence, because this is the same location, just a repeat measurements. However, another effect is very hard to remove. That's the local time. This is because the local time and the lunar phase are overprinted due to the synchronization of the rotation and optical period, right? So I think we can understand if during the orbiting and rotating of the moon is synchronized because it's tidally locked. So the local time and the lunar phase are overprinted. We have to remove the effects from the local time. This is the most hard part, to remove the local time effects to see the phase curve effects. So I used this a big assumption. I use the diurnal trend on the far side, because the far side are not affected by the magnetotail, and I use the same diurnal trend to correct the diurnal trend on the near side. So keep in mind, this is a big assumption, but I think this is a robust assumption. I can demonstrate a little bit later. Some trend we need to consider. The first one, like I mentioned earlier, I don't see any clear dependence on composition. So this is the global map projected on spherical observation, focus on the near side. And on the left, this is a water content versus longitude. So this is a kind of average of low latitude, like 35 degree to 35 south degree, north degree zone. Just do a global average at each longitude. What you see here is there is no clear difference between the Mare dominant region versus the far side highland region. And there's some specs in PKT region that could be due to like localized anomalies such as periclite deposits. And generally, you don't see a clear compositional dependence. And so this is why I think we can assume the diurnal trend between the near side and far side can be the same, even without any effects of magnetotail. And the second one is the diurnal variation, as I mentioned. So this is the observation at the same location on the far side. just a repeat observation at a multiple local time of the lunar day at a similar location. I just split into 3 different latitude zone, low latitude, mid latitude, and high latitude. I use a 30-degree as a boundary and a 60-degree as a boundary. And I will apply this trend to correct the downward variation on the near side. As I mentioned, there is some like optical maturity dependence, but because we're examining the same location, so this won't be an issue anymore. Yeah, a second variation. This is a very strong one. We see a strong latitudinal dependence. You can see near the 0 degree, that's like only a few tens ppm, almost nothing. But it goes to polar region, you see like close to like 1000 ppm. I break down 3 different latitude zones, like I mentioned before. So like 30-degree north to 30 degrees south, this is a low latitude. You can see the water content at this zone is very low, only few tens ppm to like at most 100 ppm. So this can be into one zone, and the mid-latitude zone from 30 degrees to 60 degree on north and south hemisphere. And then high latitude, I use 60 degree to 75 degree. I didn't use any data from above 75 degree because the strong topography effects and the shadowing effects. Okay, let's look at some results part. So this is first look at the highland, and the red plot, the red figure. This is raw data without any correction. This is a very basic figure, but I want to point. I can explain slowly. So for each color, they are from the same region. There are overall 12 different regions with repeat observations. And you can imagine the lunar surface is not always homogeneous. The water content can be heterogeneous due to a lot of factors, for example, optical maturity. But overall, you can see the dashed lines for each region. The trend is the same. The diagonal trend is the same as the near side. And then we can use the trend, they parallelly shift up and down due to the background of water difference. But anyway, we can use the trend to detrend it, as shown in the left plot. So after remove these diagonal effects, this is what you see here. So what the water content versus I plotted to lunar faces now. But after the detrending of the diagonal variation, you can see it's almost consistent. So it's close at 150 ppm, plus minus like around 7 ppm. So very small variation. You see the arrow bars, but the arrow bar is due to heterogeneity of the whole zone, because we are beaming the whole zone. The same zone, you can have fresh craters, you can have like mature regoliths. So the water content can be very heterogeneous. So the arrow bars only represent the heterogeneity of the zone, but it doesn't mean the water. So overall, after remove the diagonal variation, you see like a relatively flat line. So there is no any clear variation when the moon across through the magnetotail. However, as go to the mid latitude, the story is different. Again, this is I didn't show the raw data, but if you're interested, you can look into the paper that's in the supplementary material. This is after the training. What you see here is the water in the solar wind, typical solar wind, and it then goes up when the moon goes into a dust magnetosheath, and it's almost flat in the magnetotail center, and increase again in the down magnetosheath, and then into the typical solar wind. The variation in the dusk and down magnetosheath is greater than the mapping uncertainty. I think this is associated very well with the 50% higher proton flux, if you recall in the first few slides I mentioned. So the Artemis measurement suggests the proton flux in the dusk and down magnetosheath is around like a 50% higher than typical solar wind. So this is consistent with a lot of like previous suggestions. The formation process can be fast, and also due to solar wind implantation. So when you increase the flux, you have higher water content. This is like consistent very well with the previous findings. And more interesting is in the tail center. So water varies very little in the tail center. You can see almost like a consistent line. Because they're like a heterogeneity of different regions we studied. So you can see the error bars, you can see the spread, but overall you don't see drop. This is very interesting because in the mid-latitude, the moon stays in the tail center around 4 Earth days. And during the daytime, like a local, like noontime, it can have like 370 K or even higher temperature. You heat up some sample in a high vacuum for 4 days. And there's no proton implantation, but you don't see any water drop. This is very interesting, right? And this is some more details about the mid-latitude, the magnetosheets, high water in magnetosheet example. Figure A shows several observations at the same zone at a different local time. What you see here is like when the moon is in solar wind, it's follow the same diurnal trend as the far side, but you can see the magnetosheet trend is totally different. That's outlined by the blue dust box. You can see they are above the diurnal trends. They show higher water content than the typical like a solar wind diurnal trend. That's suggesting the water formation rate is higher. And figure B, this is more direct evidence because this is a 3 repeat measurements at the same location. So the first circle is in solar wind, second one in magnetosheet, third one is in magnetotail. The gray dashed line is the diurnal trend. So if there is no magnetosheet, it will follow a trend like this. But it turns out the magnetosheet observation show much higher water content than in solar wind and in magnetotail, and particularly compared with the solar wind, because this is like even closer to the local time. That means you suffer like a higher temperature heating, but at the meantime you're still showing higher water content than like earlier morning observation when the moon is in solar wind. So this is suggesting like there's definitely some like unrecognized processes are going on why you can have like such high water content in the magnetosheet. Well, this is clearly now we understand it is consistent with the 50% increase of solar influx. And this is a low latitude, 30 degree north to 30 degrees south. So this is not a very clear trend because, overall the water content is very low, like, few tens ppm. And also some regions are, very heterogeneous in the water content. But anyway, the red figure showing the raw data without the correction. This is versus the local time. Again, different colors represent different regions. You can see like, mostly 2 observations at the same regions. Only a few showing like 3 observations at the same region. But anyway, the dashed lines are the diurnal trend on far side. They just systematically shift up and down due to the background difference. Again, this is a log scale, so that's why your eyes don't show like a parallel, but if it's linear, it's parallel. But anyway, after the training, this is what you get on the left figure. It's kind of like a little bit similar to the mid-latitude, but not a very well pronounced. So you can see slight difference in the dusk magnetosheet. You can slight difference in the dawn magnetosheet, and there's no big change in the magnetotail center. Or you can see mostly there is no big change from the solar wind across the magnetotail and out of the magnetotail. There is no huge change because it's close to that mapping uncertainty. But I still argue maybe the dusk and dawn magnetosheet you have like a slight like an increase that's due to the proton flux increase. And also, again, the most interesting part is the magnetotail center, because in the low latitude, the daytime temperature even higher, right? Close to 400 Kelvin. And for a few days, you heat up and without any solar wind proton implantation, but you do not see a water drop. That means you don't lose your water. Heating and a high vacuum at a high temperature for a few Earth days, you don't see a drop of water. That's kind of interesting. Yeah, so this is a kind of like a summary of all the trend in the high latitude, mid latitude, and the low latitude. Again, the trend in the magnitude in the magnitude shift in the dusk and dawn shift seems consistent well with the increase of solar wind flux. The most puzzling part is in the tail center. Why you don't see a decrease in the tail center? Because the solar wind ion flux drops like to less than 1% of typical solar wind, but you don't have proton implantation. When you heat up your sample and have vacuum, you're supposed to see a drop in the water, but actually you don't see it. So this is like a suggesting like highly suggesting like some like unrecognized mechanisms of water formation, not due to typical solar wind proton implantation. So then I go back to understand more about the configuration of the magnitude shift. And then I read this paper by Jasper Alicus. They suggest that this is based on like RP observation. They suggest that the moon can stay in the plasma sheet for like over 40% of the magnitude time. So if you imagine, okay, this is the figure A I showed before. You can imagine there's a north lobe, south lobe, and then there is a plasma sheet. Well, actually, the moon, because the plasma sheet is on the plane on the Earth, like I forgot what's the name. Yeah, but anyway, the moon orbit, the lunar orbit aligns well in the plasma sheet position very well. So you can imagine why the moon can stay a lot of the time in the magnetic sheath, but not all the time because the magnetic sheath it's not the shape is not well defined, so it varies a lot. So I think that even the 40% is kind of like approximation because it really depends on how the plasma sheet is developed. What's the real position of the plasma sheet? But anyway, it's the moon stays a long time in the plasma sheet. And then I asked Andrew help me to pull out the ion the charged particles flux in the plasma sheet as shown in the red figure. As I saw this figure, I recall immediately what Tom Orlando told me like back to few years ago. What he said, oh, what does the electron role in the magnetotail? If the solid lines are electrons, you can see in the magnetic sheath, in the magnetotail, the electrons still show very high flux and also still show very high energy. But this is a solar wind. So the black line is solar wind. You can see the energy is very low, like a few EV. So that means like, even though the flux is high, because you don't have enough high energy, just stick on the surface and go back again. But the KeV electrons is very high energetic. It can play a big role on the radiation effects. So this is where we think, oh, maybe the electron plays a big role on the water formation because of the irradiation of the electrons. Well, if you look at other species, for example, the dashed lines are ions, the flux is much, much lower. Even though the plasma sheet is like no more than 5% of the typical solar wind. So even though the energy is high, but the flux is too low. So like a few percent or 5% of flux in typical solar wind, that's too low to account for like, the similar effects of solar wind implantation, typical solar wind implantation. However, the electrons, like both energy and flux, are equivalent to the ions in typical solar wind. So we think this is possible, like, the electron irradiation may play a big role on the water formation. So next step is going to do some like experiments to test this hypothesis. And there's an alternative hypothesis to explain this trend. On the red plots, this is a low latitude and mid latitude. The symbols showing number means they are in the magnetotail. So that's the lunar phase. Because I cannot plot the lunar phase with the local time at the same time. So I just plot water content versus local time. And then if in the magnetotail center, I just put numbers. That's the phase. So what we observe here is more than half, like over 50% of MQ data in the central magnetotail were acquired near the local noon. So then, as the discussion with the Bill Farrow and O.J. Tucker, and they suggest that it's possible there's some like a low bonding energy hydrogen, like happened in earlier day of the lunar day. It can be diffused very fast before entering the magnetotail, while only like a high bonding energy hydrogen can be retained on the surface, but they are very hard to diffuse. So then this can be used to explain why there is a small variation in the magnetotail center, because most of the observation is near the local noon time. Only high bonding energy hydrogen left, as shown as outlined by the red circles. However, there is some observations not in the local noon, like in the early morning, like around like 9:30 local noon time, early morning time. But it's interesting. They also they do not show like a lower water content. They show higher water content or equivalent water content compared with the regions in the solar wind. But this is hard to understand because this is like in the tail center. You don't have implantation, but this is not a very early morning. This is like 8 or 9. This is 9:30. So it's like after like a few days exposed to surface, even though the temperature may not be high, but at a low latitude, it can be very high on a 9:30 morning time, while like without any plantation, but you don't see a drop of water versus compared with like other regions in solar wind. So this is kind of like a puzzling question to answer if this is due to diffusion. But I think maybe OJ and Bill have different answers now. That's kind of like a future study to understand whether we can just based on the diffusion process to explain the observed trend. And also, this is not a conflict with the electron radiation, because during the radiation of electrons, it can also cause like a heating, like a high temperature. It may also increase the diffusion process. Yeah. Okay, so this is a summary. This is my summary slide. So at the low mid latitude of the moon, we observe some interesting trend for the water, lunar surface water variation. It increased in the dusk and dawn magnetosheath. This is due to the increase of solar wind flux by around 50%. And it exhibit no decrease in central magnetotail and heating and no implantation of protons. And this could be due to like unrecognized water formation process by radiation of high energy electrons, like hundreds of eV to keV electrons in the plasma sheet. And also we are going to test this hypothesis based on radiation experiments. And also, there is no strong magnitude effects at high latitudes. I think this is due to maybe lower temperature and the water formation there is more stable across the lunar day. And I think future continuous simultaneous observation of water and solar wind are necessary to understand completely about this process. I think the coming Trailblazer mission will have to perform like a full cycle observation. You can see we have to use a combination of 12 different zones, like regions, to show the trend. And in future, like a Trailblazer can observe the same region during the moon's passage through the magnetotail. I think that would be super helpful. And also observe like a region on the far side for the diurnal trend to confirm whether it's similar to what MQ observed. And then we can use the trend, the local time trend, to correct the near side moon to understand the magnetotail effects. And I think this work has a lot of implications. For example, it is important for understanding similar processes on other Alice bodies. For example, like Vesta, Mercury, Venus, Rigel, and others, because the high energy electrons in the solar energetic particle events can show similar effects as the plasma sheet, because the energy that energy range can be similar, like from hundreds of keV or even higher. And also it occurs frequently, in past like the science lifetime. So it may cause some like high energy electron radiation on these kind of Alice bodies, and may have like a water formation on them. Okay, that's it. I think I'm happy to take questions now.
Awesome. Thanks, Shuai. All right. I can see the virtual applause. And yeah, so what questions do we have for Shuai? And so feel free to raise a hand or put a comment in chat, however you prefer to ask a question. So while folks are warming up, I'll ask one. So Shuai, I think you said this, but I'm trying to wrap my head around it. So what is the reason that the variation is strongest at mid latitudes and not at high or low latitudes?
Yeah, that's a very good question. I think I do not have a clear answer to you. But my understanding is at high latitude, that's easy to understand because the temperature is low, right? So it's like, during the daytime, like highest temperature is still very low. And the temperature controls the variation of hydrogen. So that explains, I think, high latitude. While low latitude, low is because the water content is too low at a low latitude. From like Apollo sample, from China sample, also just like only a few tens ppm, right? And you can imagine our detection limits, like, for example, MQB instrument, I would say maybe 10 to 20 ppm, that's a detection limit. Well, you only have 40, 50 ppm water in it, even though you have a strong variation, but that's observation shows like not very strong. In a mid latitude, first, water content is high, right? So it can be a few hundred ppm. Second, the temperature can also be high because even at a 45-degree during like a local noon time, for example, like around 5 during their observation, because they close to the local noon, they suggest that can be like close to 375 Kelvin, the peak temperature. So you can still have very high temperature during across the lunar day and high water. So that's why I feel like that's the reason why you observe like a stronger variation in the mid latitude.
Okay, so you're saying at the high latitudes, because it's cold, like the water sort of tends to accumulate, and so you don't see differences during the magnetosheet passage?
Yeah,
okay.
and also keep in mind, and also the solar proton flux is a cosine of latitude, right? So it's like the rate will be also lower, but
okay,
because it can be retained, even though the rate is lower, so that's why it can accumulate more than mid latitude and lower latitude. So that's why you see a latitudinal dependence.
Okay. Yeah. That makes sense.
Well,
Yeah,
that's just my thoughts. So like a lot of things I think we need to demonstrate, like go there to do observation.
Yeah, no, that's
or more
that's
high
really cool.
latitude samples.
Yes. And so one more question. And folks, if you have questions, please feel free to raise a hand or put it in the chat. But so could you, I know you have this in the paper, but how exactly does the electron irradiation formation of water work? So with protons, it's kind of like I feel like it's more intuitive. So you have H plus coming in and it reacts with O and it forms OH.
Yeah.
Like I know you discussed this in the paper, but how does the electron thing work?
First, we do not understand clearly. We just discussed in the paper, right? So our thoughts are there are a few effects. First, there could be like a free hydrogen, like H2. So electron can help to break down to H atom. H atom is easy to move and react with the surface. Second, because it's a KeV electrons, it can cause radiation effects, right? So for example, form defects. And then with more defects, it's easier for like a hydrogen move around. And a third one, because there previous exists like defect locations, the electrons, because it's KeV, so it's may penetrate deeper, so it can be trapped. If it trapped in some like a region, like more electrons trapped there, it can cause like a negative potential, right? So you can imagine if you have a negative potential, and then the protons, the pre-existing protons, can move around, like enhance the movement. And then during the movement, it can have a more chance to meet with another oxygen defects and then form OH or even H2O. The fourth one is related to the diffusion process. So I think Bill mentioned in one of our discussion, what he suggests, there are some studies showing even the high energy electron radiation can enhance the diffusion process. So the lunar, there is a assumption there is the lunar surface should be rich in H or H2 in the magnetotail. That's from accumulation of a previous, billions of years implantation. Yeah.
Okay, yeah, no, thanks. That was a good explanation. Yeah. All right, what other questions do we have for Shuai? I know there are questions.
This is Monday. Everyone is busy.
Yeah. Go on, folks. I'm gonna sit in silence until someone asks a question. Because I know this is a good turnout. So this is like more than we've had for the last few telecons. So I know there's a lot of interest.
Yeah, or they can email me afterwards if they have
questions. Yeah. All right, I'll ask another one. So like, is there, so you mentioned the experiments and your potential future work to validate this. And okay, so I'll hold on to that question because I see Carly has a question in the chat. So Carly says, great talk, Shuai. What experiment would you propose to have on the surface to help understand the process that occurs, or the processes that occur?
On the surface, that's really great. So, only two instruments: spectrometer, like a Bethany's true laser spectrometer, would be great. And then another one will be like a ion probe. So to monitor the surface plasma environment. For example, specific like protons and electrons. You just light you don't need a rover. Maybe just a liner will be enough on the surface, and it just watch during the moon passage through the magnetotail. So you walk simultaneously. So similar to lab experiments, because in lab you can control your ion flux and electron flux. You also at the same time you have in situ spectrometer observation and see how the water feature varies. So while even better on the moon because it's provide like a high vacuum without any contamination. A second is like the Earth's copy to control the ion and the electron flux. So you do the experiments on the surface naturally, just sit there, observe. That would be great. And if you can do a multi-latitude, that's even better.
Yeah, very, very cool. So so what I was gonna ask something similar, but so there is a rover lunar vertex that's planning to go to a lunar swirl.
Yeah.
And so based on and I'm just thinking like it's a magnetic environment that's exposed to the solar wind, but are there any specific parts of this that lunar vertex could help to ground truth?
I talked to David summertime. It's so sad that they don't have a spectrometer. They have a spectrometer, but they don't have a spectrometer covering the water bands. So that means I think they can observe how the plasma environment, but I don't think they can do any a monitor of the water variation. So that's so sad. If you can't have a spectrometer like a tube laser we have, that would be great. Yeah, so that's also even better because that's additional factor, right? So that's the local magnetic field. So it's a rover, so you can just stand in the solar wind, watch the moon's passage through the magnetotail, and then when the moon, the sunlight, it can also go to the local magnetic field region and see how the plastic environment change. So yeah, it's yeah.
Yeah, and sorry, I'm typing at the same time. And on a asking, yeah, I was just replying to Bethany saying that we'll share the recording afterwards in case folks weren't able to catch all of the presentation. But on a similar note, so with Viper, for instance, like I know that's and some of the other CLIPS landers as well. Like I know those are high latitude missions, and you don't see as strong a variation at high latitudes in general. Would
Um,
would you expect that to be different? Like, are there sort of specific regions near the poles? Like, maybe if you have kind of sun-facing slopes, would you
yeah,
expect to
yeah,
see some of
that's a
the
good point.
same processes?
Yeah, do you know like what's the slope? How what's the deepest slope Viper can climb? I think I asked uh Connie before, but I forgot the number. Sounds like it's not a very super deep slope, right?
Yeah, Caleb or Ariel can correct
Oh,
me, but I
15
think it's like
degree.
15. Oh, yeah, yeah. Thanks, Caleb.
Yeah,
Yeah.
at 88 degree latitude, 89-degree latitude, minus 50, that's 73. Yeah, I would not expect to see like a very strong variation.
Hmm.
Um,
Okay.
yeah, and yeah, but it's worth a try. And do they have a uh spectrometer to measure the charged particles? I guess they do, right? The like ion spectrometer, like a mass spectrometer. If they can do like both electron and proton flux measurements,
Yeah,
that would be great.
I'm not sure what the and if someone knows, feel free to speak up. I'm not sure if Viper will be sensitive to electrons and ions. So the mass spectrometer is I think it's like 1 to something AMU, and
Okay.
it's mostly focused on neutrals. It's also looking down at the surface, and so it might miss some of the
Oh, right. Yeah.
incoming
Yeah,
flux.
you have to yeah, if you look down, but it's still I think they will see a trend because um you know it's landing on the near side. So it's like during the passage of the magnetotail, there is a strong variation in the magnetotail lobe and also magneto sheath. I think they should see like a very nice trend for reflected like protons, like H plus. Yeah, they
Mhm.
should see the trend, but uh, it is worth. I think it's worth to do the to do the observation. If they will have time. Like because the whole a whole cycle will take like around two no like more than 1 week Earth day, so more than 7 days on Earth from solar wind go through the magnetotail on the other side of solar wind. Yeah, it will take more than 7 days. Not sure they are willing to do that because they may need to sit on a like slope, bio-illuminated slope, and then do the monitoring. That's kind of waste of. But during charging, right? I'm not sure during
Right,
charging
yeah, yeah.
they are allowed to operate.
Uh-huh. Yeah,
Yeah.
that's a cool idea. All
Mm,
right, what else? So we have time for maybe one more question. Okay, people are quiet today, but that's
yeah.
must be because I'm asking such good questions. Okay, I'll ask you one last one, Shuai. So
Sure,
Shuai,
sure.
so you've been working on, various aspects of this for a long time. So, I guess in general, you know, what do you think? Are we close to understanding the this how the solar wind creates hydroxyl? Do you think like there are key pieces missing? But yeah, what's on your mind?
I feel like we still have a lot of unknowns, but we are close now. Uh, there are like a still like a few important trends we need to confirm. For example, the diurnal trend. I know there is still a lot of dots in the community, but there are multiple. Currently, we have a multiple observation now. Just the observation showing like the formation is very fast, lose is very fast, and there are lab experiments showing that trend too. But it sounds like it's chemically, it's very hard to understand why the amplitude is huge, right? So we observe like few tens ppm, like in the mid latitude there's close to 50 to 80, highest 80 ppm diurnal variation in only a few Earth days. I think I had a lot of discussion with Carl Habes before, like, he always reached to me. I feel like that's a big unknown because, based on our current, like, chemical model, it's hard to explain why there's a huge variation. Bill's model can explain, like, based on diffusion, sounds like, they can explain well. But anyway, this is like, we need a more, either data or more experiment to understand the chemical way why our observation is showing like such a strong diurnal variation. The second part I think related to water ice. It's kind of like a mystery why the polar region showing like such low water ice. Because we see like this kind of like a strong downward variation. We see like water moving like either OH, either H2 or H2O moving. OH may not move, but we see some movement on the surface. But remember, this is like even based on recent Norbert work, like even like the PSR could be like it's only billions of years, 1 billion years, but still a very long time, right? So you should still be able to accumulate something there. But it's kind of like a mystery why they don't go there, or where do they go? Where did they go? Yeah, so it's like I feel like multiple latitude observation, or like orbiter like IRO give me 10 years like water observation. That would be great. Yeah.
Yeah, I agree. All right, so we are at the top of the hour, but thank you, Shuai, for great talk. And I'm sure people will reach out afterwards if they have questions. I think it's
welcome.
just like it's just like you've gone so deep into this data set that that I think the reason people aren't asking questions is because everyone wants to kind of try and wrap their head around it. But this is really cool stuff.
Thanks.
So yeah, thanks Shuai, and thanks everyone for calling in, and have a wonderful holiday season and a good time at AGU if you're attending. Please take notes, and we'll see each other in the new year, if not sooner.
Yeah. Okay.
All right. Take care,
Understood.
everyone. Bye.
Bye.